Use Newton's law of universal gravitation to find the gravitational force between Earth and the Moon. The mass of the Moon is approximately 7.3477 times 10 to the 22 kilograms. And the distance between Earth and the Moon is 384,400 kilometers. So in order to calculate a gravitational force, we have to have two masses involved. This is going to be the Earth, and this one can be the Moon. We need the distance between them, and that's 384,400 kilometers, or in other words, 384 million meters. The mass of Earth is 5.97 times 10 to the 24 kilograms. And the mass of the Moon is 7.348 times 10 to the 22. Now, Newton's law of universal gravitation has a formula Fg equals G m1 m2 over r squared. But in our case, it'll be G times the mass of the Earth times the mass of the Moon divided by r squared. Now, what is G? G was 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Now let's plug everything in. Now, when we're doing these types of problems, we prefer to have our distances in meters because Newton's inherently has meters in it. So it'll work better with Newton's if we use meters instead of kilometers. As we can see here, the kilograms squared is going to cancel with our two masses, and the meters squared will cancel with the meters squared below, leaving us with just Newtons. Now, how we enter this into calculator is a little tricky. So if you have the TI 30X2S, I'm going to write out how I would enter it on that calculator now. We'd want to use the second button and the x to the negative 1. Above that, you'll see there's an EE. This allows us to enter scientific notation in a very easy way. What we want is we want 6.67 e negative 11. Okay, and then we'll multiply by 5.97 e24. Multiply that by 7.3477 e22. After that, we're going to divide by 3.844 E8, and then we'll square that. Now, the great thing about using this notation with the calculator is the calculator will treat these as just single numbers. You don't have to worry about any order of operations issues. Like for example, this is not going to just square the 8. It's going to square the whole number. It's really useful and really the preferred way to enter something like this into a scientific calculator. Let's see what it gives us. All right, I get 1.98 times 10 to the 20. So a very large force between Earth and the moon. Now, what does this result mean? It means that Earth and the moon will have an interaction called a gravitational force. And by Newton's third law, it's not just one force on one object. It's a pair of forces. And they're actually equal and opposite. This one will be Fg Earth on moon. And this one is Fg moon on Earth. They're what are called a Newton's third law pair. How can you tell a Newton's third law pair? Well, they'll have the same magnitude in the opposite direction, where the one object acts on the other, and then the other acts on the first object. Next, we're asked to find the strength of Earth's gravitational field on the moon. Now, just for fun here, let's try to find the value for G here on Earth's surface. And then we'll compare it to the field strength way out at the moon. Now, what do I mean by the field strength at Earth's surface? I mean if we're located right here. How would we find such a thing? Well, we would actually use Newton's law, but without putting in that second mass. It'll be big G times the mass of the object that's exerting the field, and then divide by the distance to the point where you want to evaluate the field. So that would be Earth's radius for this problem. All right, so what do we get? We get 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Multiply that by Earth's mass. And then we'll divide by Earth's radius. And then square that. So the value of G at Earth's surface, according to Newton's formula, (9.81). But now let's go way out to the moon. How strong is the field of gravity out there? Now, keep in mind, we're doing this based on Earth's mass, not the moon. The moon will actually create its own gravitational field. We want to see how strong the field is due to the Earth. So for that, let's use Newton's formula. We'll use the mass of Earth once again, but this time we want the distance. But this time we want the distance between Earth and the moon. Okay, it's going to be 6.67 times 10 to the minus 11 Okay. Point 0.0027 newtons per kilogram. Notice that when we use this version of the formula, we don't put a second mass in there because it's about how many newtons mass would feel if it was there in the field. And also, the kilograms squared cancels with kilograms. That leaves us with 1 kilogram in the denominator. And we now have what's called our gravitational field strength out at the moon. And notice how it's a really small value. That's because the strength of the gravitational field decays rapidly as you move away from Earth's center. And the reason behind it is that we have that inverse square relationship. So as we double the distance from Earth's center, we would actually cut the gravitational field strength by a factor of 4.